I'm Richard Hollingham. Welcome to the Planet Earth podcast from the unlikely setting of a hospital accident and emergency department where natural world science is being used to diagnose disease. Also this time, putting a value on nature.
How many conic ponies do you need to change the vegetation in such a way and keep it in a particular condition that it's the best possible condition to stop flooding?
Just come through into the brand new Diagnostics Development Unit in the Emergency Department of the Leicester Royal Infirmary. And really, it's a room full of equipment and absolutely no patients. The sort of equipment you would expect to find in a physics laboratory rather than the emergency department of a hospital. Now, this unit is designed to smell, look and feel disease, and it uses technology developed by the University of Leicester for environmental sensors. Well, with me are Paul Monks from the university, Professor of Atmospheric Chemistry and Earth Observation Science, and Tim Coates, Professor of Emergency Medicine here at the hospital. Paul, you should explain, what is all this?
Well, this is our technology that we use for non-invasive diagnostic development on patients. So we've taken instrumentation that we use in the laboratory and outside in the environment for actually smelling the air, sniffing the chemicals in the air, and we're now using it in the hospital environment to smell people's breath.
So what is the setup here? There looks like just computer monitors there, a camera stand, a tripod there. Now this, I recognise, is a mass spectrometer, so you can analyse individual chemicals, a series of long metal tubes, complicated piping and the like.
Yeah, well, what you've got in front of you is a state-of-the-art, what we call a proton transfer reaction time of flight mass spectrometer, but it's a way actually of measuring and weighing molecules very, very quickly. So we can take the molecules coming out of your breath and weigh them and actually look at the composition in terms of the chemical composition of your breath. And what we hope to be able to do with that is actually smell disease.
And I said I recognise this because I saw something very similar in a laboratory analysing air for pollution.
This is exactly the same technology that we'll actually be deploying later this month into London to measure the air pollution during the Olympics. So the same technology that we developed for sniffing air quickly, we now use for sniffing people's breath.
Now, Tim, we're in a room full of this equipment, but on the other side of this are the bays where there are patients coming in as we speak, being attended to in the emergency department.
That's correct, and we've got a series of ports through the wall here, both electronic and physical, so that the patient, the other side of the wall, can be monitored using the equipment in this room. Now that means that the doctors and nurses in the emergency department can continue treating the patient while the monitoring's going on. So even the sickest patients can be in there and we can be monitoring them. Now that's something in the past that's been really difficult to do.
And how are you using this? Who is this for?
We're using on a range of different patients just to see what sort of results we get, because a lot of this technology is new to humans. But for example, a patient with a chest infection coming in, we know that different bacteria produce different molecules. We can sniff those molecules using the mass spec and perhaps tell which bacteria is in a patient's chest. Now that might help us give them the right antibiotic for their infection. We don't know that we can do that, but that's the sort of potential we're looking at.
And are you going to identify particular patients coming in and trying them out on this?
So we've got a set of studies that are going to go on. We're looking at specific patients that we think are going to be have some sort of benefit from this sort of technology, and then we get consent from the patients, ask them if we can spend about half an hour. It's all non-invasive, so it doesn't involve any of the unpleasant things we do like blood tests and so forth. And it's amazing, you know, patients, even when they're ill, most of the time they're quite happy for us to be monitoring them and to be doing research that they know is going to benefit other people.
And you mentioned that this is non-invasive. So you've got the tubes going through the wall. What do patients do? What do you attach to them?
So they have a mouthpiece that they breathe in and out to get the breath sample. They also have a series of stickers that we put on the body. We have a series of cardiovascular monitors, again, non-invasive new technology, to monitor their heart. So we're really looking at their heart with the cardiovascular monitors, their lungs with the breath analysis, and then we're also doing some imaging. You mentioned the camera and tripod. That's a hyperspectral imager, which has been translated across from space science. We're doing a battery of different tests on our patients.
So this is from partly space science, partly from atmospheric monitoring. Paul, how did you decide to put them all together? Because surely that's the key to this, is you're actually doing several things at once.
Well, as with all the best things in science, it's serendipity, and it's really a conversation in the corridor. We'd been actually doing the breath analysis for a while in a very minor way, and then I bumped into a colleague in the Space Research Centre and said, well, we've been doing this, do you fancy doing something with your imaging? He said, well, actually, we've been working on that. And then we found Tim, somebody from the medical profession. And as with all the great things, it just kind of came together, and we decided to do this. And then, very kindly, the university gave us £500,000 to buy the equipment to do this. And since then, it's mushroomed. It's really a land of opportunity for doing really cutting-edge and breaking science.
And Tim, do you anticipate actually being able to diagnose some diseases with this? Will you talk about analysing breath, analysing bacteria, or is that a long-term goal?
That's a medium-term goal. I think a lot of science people tell you, hey, there's a breakthrough and, it's going to do this. And they're talking 5 or 10 years away. With this sort of technology, we're talking probably about 2 years away from having something that we can really be testing to see whether it makes a difference on patients.
You've got, just as we speak, there are trolleys going backwards and forwards. And this is early evening. So you'd imagine this isn't the busiest time here. Could you imagine something like this making quite a big difference?
We see about 450 patients a day coming through this department. The real trick in emergency care is to pick out which of those patients are really sick and need emergency intervention, and which actually aren't so sick and can go to their GP or to outpatients. We often have difficulty in making that decision, and we sometimes get us wrong. So technology like this, if it can help with that decision making to pick out patients that really do need our help so that we can concentrate on those patients, that's going to be a benefit.
Tim and Paul, thank you. And later in the Planet Earth podcast, we'll be putting this equipment to the test on me. We'll get some fresh air first on the Humber Estuary near Goole in South Yorkshire. I went there to meet Dave Raffaele from the University of York. Now, Dave's the head of a major national 7-year project to investigate the link between biodiversity and the services nature provides, such as food, clean air, water and flood protection.
This is the RSPB's Blacktoft Sands Reserve. It was set up originally as a wetland habitat because of its interest for the birds, particularly marshland birds like marsh harrier, avocet, herons, egrets, but also, as you can hear in the background, warblers and black-headed gulls and things like that.
Now, we're sitting down in, I suppose, an open-air hide. There's no roof, but we have got a slit that we can look out across the water here, the reeds, the various types of duck there, and a pony in the distance. I think we should mention the pony.
Yeah, Blacktoft Sand's rather unique in this respect because it holds 4 individuals of something called a conic pony, and these are almost wild animals, and they're here, been introduced really to help with the grazing regime of the marsh to improve the biodiversity of the vegetation. But they're also of interest in their own right because they're very close to some of the wild horses that we used to have in Europe about 5,000 to 7,000 years ago.
So beyond the reeds, we then have the river itself, and we're at the confluence of the River Ouse and the Trent.
That's
so
correct.
Flowing from Nottingham and then down from York and into the Humber.
Yes, and of course that means there's an awful lot of water. The Humber itself probably drains about 1/6 of the land area of the UK because of the Trent and the Ouse and all the rivers that flow into them. So there's a lot of water comes down here, but also within that water there's a lot of sediment as well, and that's what produces these vast marshlands and mudflats which we find along the Humber and make them such interesting areas for nature conservation, but also scientifically as well.
And you're interested as much in the biodiversity and what's here and this stunning view and all the nature here as the hidden benefits of that nature.
Yes, if you look out at the area we're looking at the moment, you can see it's dominated mostly by reeds and Phragmites, and these have many, many functions in the natural environment that people don't really appreciate. Traditionally, they were used for thatching, for making roofs and so on, but they have many other really interesting functions. So They provide a kind of soft engineering for storm surges and for wave action and so on, which means we don't have to build solid seawalls, so they take the energy out of the waves. They also filter water before it goes from agricultural land into the rivers and strip out all the nitrates and so on. So they have a purification function, they have a storm defence function, as well as providing lots of biodiversity for us as well.
And these sorts of functions, they're termed ecosystem services, and that's what your project is investigating and looking at. It's a rather ugly word, but I suppose it describes what it does.
Yes, I think the best way to think about them is that nature provides lots of benefits for us, and this is one of several habitats we're looking at in the United Kingdom. So we're looking at coastal marshes like these, we're looking at upland rivers, we're looking at lowland farms, and we're looking at urban areas as well down south in England. And we hope to extend that to many other kinds of habitats. And each of these habitats has lots of biodiversity which provides those kinds of benefits for us. Food production from agricultural land, biodiversity provides that for us. In an area like this, there's lots of recreation provided for us as well as climate regulation in forests and so on. And what we're trying to do is find out how much of that biodiversity you really need to sustain those benefits in a changing world.
So are you trying to quantify this, to put numbers on this, to say, right, we need this many reeds to stop the flooding here, or we need this diversity of plants and insects?
That's right, and unless we quantify those, then they won't be valued properly in decision making. So many of these so-called benefits from the landscape, these ecosystem services, they don't actually have monetary value attached to them because we can't trade them. But actually, if we didn't have them, then we would have problems of flooding, they would have problems associated with climate change, carbon sequestration and so on. And we're trying to put numbers on those so that when we need to make decisions about the way we manage our landscapes in the UK, we can do that on a properly informed basis.
And so when we peer out through this slit across the water in front of us is almost like a pond. It's so still today. There's no wind at all. Then there's the reeds, and then there's a butterfly just flitting past. There's the pony in the distance, and then the river, and then into a sort of haze of the hill and trees. You put numbers and say, right, we need that, and that'll mean we get this amount of benefit from that.
That's right. So the kind of trade-offs that people like the Environment Agency, for instance, have to make on a daily basis, but we all do in society, is what should we do about whether we want to build sea defences to stop flooding or river defences to stop flooding? And one of the decisions we might want to make is not to invest huge amounts of money into those sea defences, but maybe to purchase adjacent agricultural land, which also has monetary value, in order to let that land accommodate the flood, rather than trying to stop it and then pushing the water further downstream. So that's why we're trying to put the numbers on these benefits, so that people can have a common currency, if you like. It doesn't have to be money, it can be anything, but a common currency to provide a rational basis for actually making those kinds of decisions.
Now I'm just watching that pony over there, swishing its tail, swishing the flies away, grazing on the marsh. I guess it's grazing on some grass or sedge or something over there. How do you put a number on the benefit of that grazing, or benefit or otherwise of that?
Well, that's what the project is really all about. What we want to know is, and that's a very good example for this conic pony, is how many conic ponies do you need to change the vegetation in such a way and keep it in a particular condition that it's the best possible condition to stop flooding? Because although it all looks like reed here, there's many, many species. And the central question is, how many species of these reeds and sedges do you actually need in order to provide that benefit of flood regulation or water purification for us? And, of course, the conic pony is one of the moderators of that biodiversity, because by feeding selectively they can increase the diversity or decrease it. So that's a very good example of why biodiversity is important in these questions.
Okay, so you gather all this information about literally the birds, the bees, the marsh, the river, the ponies, all this stuff. How is that used?
Well, this kind of information is fairly attractive to policymakers, and that's evidenced in the recent government white paper on the environment, which is all about the value of nature. In fact, that's the title of it. And the idea here is that for the first time we will be able to actually attach proper values to all the things we took as public goods, and therefore we don't attach any value to at all. And by producing this kind of information, it allows policymakers to make quite large-scale decisions about the way we manage our landscapes.
And does that help preserve it?
That's one of the things which we hope to establish over the next 7 years. There will obviously be a trade-off between these kinds of benefits, like carbon sequestration, how many tree species you need in order to do that, and the biodiversity of the wood. And what we're hoping to demonstrate is that you probably need quite a lot of that biodiversity in order to generate those kinds of benefits, because even if you don't need them today, you will certainly need different kinds of biodiversity in 20 or 30 years' time, with climate change in issues associated with population growth and food security, more demand on the land, and we will want very different kinds of biodiversity in maybe 50 to 100 years' time, so we really can't afford to lose that today.
Dave Raffaelli from the University of York. And you can see some pictures of Blacktoft Sands Nature Reserve on our Facebook page. To find it, just search for Planet Earth Online. I'll also put some pictures of the Diagnostics Development Unit here at the Royal Infirmary in Leicester, which we're about to try out. With me still is Paul Monks. What are you going to do to me?
What we're going to do is actually take a breath sample for you. What we've got just in front of us is a series of breath sampling units, and what we use that for is regularising the amount of breath. And what we're going to do is we're going to set you a target to breathe to and get you to what's called tidal breathing, which is gentle breathing in and out. Then we'll take the air and we'll put it into our mass spectrometer, we'll add some water to it, and we'll actually take some fingerprints. So chemical fingerprints of your breath, and then we'll weigh the molecules in there, and we'll check whether, for instance, you're a smoker.
I'm not a smoker.
Or whether you've got diabetes. They're very easy things to see virtually instantaneously on the screen.
Okay, well, let's give it a go. So this is the mouthpiece. It looks, I suppose, like an asthma inhaler attached to a bit of piping with a long lead going off into the machine. So I've got to breathe in time to the beeping. Okay.
You should be so kind.
What you can see on the screen now as you're doing this is actually the CO2 in your breath, which is what we use as a marker in order to do that. And then on the top is the volume of air that you're putting out into our instrument. And what we're trying to do is get you here to regularise your breathing so we can get the same amount of air into the instrument. And we can see on the mass spectrometer screen behind us the chemical data coming up from the measurements that we're making.
I must say I was pretty rubbish at breathing in time with a beep. That was quite difficult.
Well, actually, your breathing's quite regular, though your volume's a bit all over the place.
Oh, okay, yes. Yeah.
So now as we move over...
So we move over to
the
the mass spectrometer, which is this shiny collection of tubes, and here's the screen with my breath analysed.
Yes, so we're actually looking at the chemicals in your breath, and we've looked at it in real time. And that was one of the real innovations of the work that we're doing, is that you can actually measure atmospheric composition, but also breath in real time. And what we've got up on the screen here are peaks like acetone, which is a diabetic marker. Also ethanol, just to check that you haven't had a drink this afternoon before you came to join us. And no, you've actually got a flat baseline of ethanol there, so you're looking quite good.
So is that okay?
Yes, you'll live.
And for a hospital environment, this is a fairly fearsome bit of equipment. I imagine it's also very expensive. You really need to miniaturise this, don't you?
Yeah, to use the words of Star Trek, we're boldly going where no person has been before. And that's the discovery phase. So actually you need big instruments with a lot of functionality in order to explore the human breath. The idea at the end of the day is actually to miniaturise these things and maybe even produce handheld diagnostics. Something like the size of a glasses case that you'll be able to breathe into. Maybe even one day your mobile phone.
So coming back to the Star Trek analogy, like a tricorder, like McCoy has.
Yeah, well, the ultimate non-invasive diagnostic, of course, is McCoy's tricorder. I'd say where we are at the moment, though, is the bed in the sick bay of Star Trek. The instrumented bed is the phase that we're at.
Well, Paul Monks, thank you very much. And that's the Planet Earth podcast. For the latest science of the natural world, do visit Planet Earth Online, and you can interact with us on Facebook and Twitter. I'm Richard Hollingham. We've learnt I'll live to present another podcast in the future. From the Leicester Royal Infirmary Emergency Department, thanks for listening.